Imagine trying to prove a really complex mathematical theorem.
Okay.
Not just sketching it out in your head, but, rigorously, step by step. Absolute no room for error.
Right. Every single logical step has to be perfect.
Exactly. Every inference, every line. Now picture an AI doing that. Not just like guessing the answer, but proving it with total certainty.
That sounds incredibly difficult, almost impossible given how precise math needs to be. But yeah, that's exactly what's starting to happen now.
And that's what this deep dive is all about today. We're looking at a really groundbreaking AI agent called Prover Agent.
Yes.
It seems to be fundamentally changing automated theorem proving. It blends the sort of creative, intuitive reasoning of large language models, LLMs, with the, ironclad certainty of formal proof systems.
Yeah, we've been digging into the research paper on this one. It's called Prover Agent, an agent-based framework for formal mathematical proofs by Kaido Baba and a team of researchers.
Right.
And it gives a fantastic look under the hood, really shows how the system works.
So our mission today is basically to unpack how Prover Agent manages to bridge that gap, the gap between that almost human-like reasoning and absolute machine-level precision.
Okay.
And hopefully you'll get a really clear understanding of why this is such a big deal, how it functions, and maybe what it means for the future of verifiable knowledge.
Sounds good. So when we talk about absolute certainty in math, the gold standard really is these formal proof assistants.
Right. Names like Lean or Coke Isabel.
Exactly. Those Lean, the rock prover, which is Coke Isabel. These systems don't just, calculate answers. They rigorously check every single inference step in a mathematical proof.
Which has to be written in their specific language, right?
Correct. And this whole idea is based on something pretty deep called the Curry-Howard correspondence.
Ah, okay. I've heard of that. It connects proofs and programs.
Yeah, essentially. It's this insight that mathematical proofs are, in a way, equivalent to computer programs. So these systems can literally execute a proof-like code, checking every single logical step with machine precision. No errors, no omissions, no kind of hidden assumptions allowed.
Which is why mathematicians rely on them to be absolutely sure something is correct. Yeah. Bulletproof.
Precisely. But that stringency, that perfection, that brings us to the challenge. Why formal proofs have been such a grand challenge for AI historically.
Because it's incredibly hard for humans to use these systems directly.
Exactly. Working with them usually requires enormous amounts of painstaking manual effort, meticulous detail. It's really time-consuming and difficult, even for experts.
So, okay, that sounds like a perfect job for AI then, to handle that tedious, super detailed work.
You'd think so. And LLMs have made amazing progress in mathematical reasoning recently. You see models from OpenAI, DeepSeek AI doing pretty incredible things with math problems.
But there's a catch, right?
A big one. This is where it gets really interesting. LLMs, even the best ones, are still prone to errors and what people call hallucination.
Right, making stuff up that sounds plausible but isn't actually correct.
Exactly, which completely undermines their reliability for something as strict as a formal mathematical proof. You just can't have that.
Even with things like chain of thought reasoning, where they try to show their work.
Even then. Eliminating mistakes completely, especially for really tough problems, is still a huge hurdle. The paper gives a pretty striking statistic, actually.
Oh, yeah.
Prompting a strong LLM, they used O3 Mini from OpenAI to just directly generate a complete formal proof in Lean for a competition-level problem.
Okay.
It only succeeded about 6.0% of the time in a single try.
Wow, only 6%. That's low.
It is. It shows their formal proving skills are way behind their sort of informal reasoning abilities.
So let me get this straight. We have these LLMs that are brilliant at reasoning, generation, but they might make mistakes.
Right. No correctness guarantee.
And then we have these formal proof assistants, like Lean, that give perfect verification but aren't really generative on their own.
Exactly. There's this huge gap between just reasoning about a problem and actually formally proving it.
So how do you possibly bridge that gap?
Well, that's precisely the problem Prover Agent is designed to tackle.
Okay.
It's described as a novel AI agent framework. It's built on this idea called the neurosymbolic paradigm.
Neurosymbolic. So mixing neural networks and symbolic logic.
You got it. It basically treats the LLM's informal reasoning and the formal prover's rigorous checking as two specialized agents that work together.
Interesting. So what are the main parts?
It coordinates three key elements. 1, an informal reasoning LLM. 2, a formal prover model, and 3, the lean verification system itself.
Okay, LLM, prover model, lean verifier.
And crucially, there's a fourth component, a kind of bridging model. Its job is to translate natural language lemmas like mini-theorems or helpful steps into formal lean statements.
So translating the informal ideas into the strict formal language.
Exactly. And that leads to what I think is the key innovation here, auxiliary lemma generation.
Auxiliary lemmas. So like intermediate steps.
Sort of, but it's more subtle. For really challenging problems where a direct proof might fail, the agent actually generates these auxiliary lemmas. They're meant to help it figure out a viable proof strategy.
Okay. How does that work? Is it like breaking the problem down?
It can be, but it also mirrors how human mathematicians work when they're stuck, right?
Okay.
You might explore a specific case or try to prove some intermediate fact that seems related, even if you're not sure how it fits into the final proof yet.
I see. So it's more exploratory.
Exactly. It's generating potential stepping stones.
And what's really striking, especially considering the results we'll get to, is that Prover Agent does this using small language models, SLMs, not the giant supercompute intensive ones.
Right, which is impressive because it achieves an 86.1% success rate on the mini F2F benchmark.
And mini F2F, that's a standard test set, right? Olympiad problems, advanced math.
Yeah, 488 problems.
Yeah.
So 86.1% is a new state-of-the-art result among methods using these smaller, more efficient SLMs.
And efficient is key here. Does it mean it uses less computational effort?
Much less, actually. It achieves this with a significantly lower sample budget, basically. Fewer attempts than previous top methods. Makes it much more cost-effective at inference time.
Okay, that's huge.
Right.
So it's not just accurate, it's efficient. That could make this kind of verification much more accessible.
Absolutely, it could really change things.
So how does it actually piece all this together? Let's walk through the workflow.
Okay, so picture the prover agent getting a problem.
Right.
First, just like a human might, it tries to prove it directly, head on.
Makes sense. Start simple.
And for easier problems, often that's enough. It uses its informal LLM to generate an informal proof, just reasoning in natural language.
Okay, like a sketch of the idea.
Then the formal prover model takes that informal proof as guidance, like a hint, and tries to generate the actual formal proof code.
In Lean's language.
Right, and then Lean itself verifies that formal proof.
Well,
if it checks out, fantastic, problem solved, done.
What if it fails? Which it often will for hard problems, right?
Yeah, exactly. If it fails, it doesn't just give up. It enters this really cool iterative refinement phase.
Refinement? How?
Lean gives very precise feedback, error messages, exactly where the proof failed. It's like a dialogue.
So Lean says, nope, this step is wrong here.
Precisely. And the prover model takes that feedback, rethinks its approach, and generates corrected versions of the proof. It tries again.
That sounds way better than just trying once and failing. It addresses that issue with LLMs sometimes struggling to self-correct, right?
Exactly. That iterative loop with precise feedback is crucial.
Okay, so it tries direct proof, refines it with Lean's feedback. But what if even that doesn't work? If it gets totally stuck?
Right. If the problem is really tough and the direct approach, even with refinement, hits a wall, that's when the auxiliary lemma generation kicks in.
The exploratory phase.
Yep. The agent starts generating multiple potential auxiliary lemmas. And these aren't necessarily just logical subgoals that you'd plan out from the start.
So what are they then?
They could be specific examples, intermediate facts that seem relevant, maybe even conjectures based on the problem's hypotheses. It's trying things out.
And you said this is different from older methods.
Yeah, many prior methods relied on having some kind of predefined proof, sketch, or plan. Prover agent is interesting because it doesn't assume the overall strategy is known right at the beginning.
It lets the strategy emerge from exploring these lemmas.
Exactly. It allows the system to gradually figure out a path forward. It really does feel more like how a human mathematician might fumble around when they're stuck.
Yeah, the paper had that example, proving n2 plus n-agase is even.
Right.
It might generate lemmas for specific cases, like n2 plus n or n2 plus 3n.
Even if those specific cases don't show up directly in the final proof.
But they help the agent find the pattern, the general idea.
Precisely. Then these natural language lemmas get passed to that bridging model you mentioned.
The autoformalizer.
Yeah, something like Camina Autoformalizer 7b. It translates them into actual Lean statements. Then Lean checks if they're syntactically correct, if they even make sense in the formal language.
Okay, so translate, then check the grammar, basically.
Sort of. And then here's the trial and error part. Each of those formalized lemmas is tackled individually.
Using the same direct proof method from before, with a refinement loop.
Exactly. It tries to prove each lemma, and if it can't prove a generated lemma after some attempts,
It just throws it away.
it discards it. Just like a human mathematician realizing a certain direction isn't working out. Explore, discard if unproductive.
Okay, that makes a lot of sense. So, prove the useful lemmas, discard the dead ends. Then what?
Then finally the agent goes back to the original problem.
Right, the main goal.
But now it has extra context. It uses only the auxiliary lemmas that it successfully proved and verified.
As, like, established facts it can now use.
Exactly. They become tools in its toolbox. And with those proven lemmas as context, the prover model tries again to generate the final proof for the original problem, again using that iterative refinement loop with Lean's feedback.
Wow. So it's this multi-stage process. Try, direct, refine. If stuck, generate lemmas, prove lemmas, discard useless ones, then use the good lemmas to tackle the main problem again.
That's the core workflow. It really leverages the strengths of both the LLM's broad reasoning and the formal prover's absolute precision, that neurosymbolic combination.
It's a pretty elegant design.
Yeah.
Okay, so the proof is in the pudding, as they say. How well did it actually perform? Let's talk results.
The results are quite strong. As we mentioned, overall, Prover Agent hit an 86.1% success rate on the mini F2F test benchmark.
Solving 210 out of 244 problems.
Right, and that beats the previous state-of-the-art for models of similar size, specifically DeepSeek Prover V27B, which was at 82.0%.
Okay, so a clear improvement, but you also mentioned efficiency was remarkable.
Yes, hugely. That 86.1% success rate. It was achieved with a total sample budget of just 2,000 attempts per problem, spread across all those stages we talked about.
2,000 attempts. How does that compare?
It's significantly lower. Some previous high-performing methods needed way more, sometimes up to like 892 attempts per problem.
Wow, so 4 times fewer attempts in some cases for a better result.
Exactly. It really shows how effective this coordinated agent framework is. It's not just brute forcing attempts, it's reasoning more intelligently.
That's impressive. Does it perform well even with very few attempts?
It does. Even with a tiny budget, just one sample attempt overall, Prover Agent still managed a 61.5% success rate.
Better than the previous state-of-the-art model with 1 attempt.
Yeah, DeepSeek Prover V27B got 58.6% with 1 attempt. So even right out of the gate, that coordination provides a benefit.
Okay, numbers are great, but they included a case study, right, on that N1 problem.
They did, yeah. Proving that for natural numbers n3, n factorial is less than n to the power of n1.
A classic kind of induction problem, probably.
Typically, yes. And when the agent tried to solve this directly without the lemma step,
It failed.
it failed. And the paper describes the reasoning trace as less focused and more exploratory. It seemed like it was kind of floundering, didn't latch onto induction.
Okay. But then it tried again with auxiliary lemma generation.
Yes. And this time, it succeeded. It generated 3 lemmas.
What were they?
The first was just checking the base case, n3. So, 3. 3, 3, and 1. That was easy to prove.
Okay, standard induction base case.
The second was n1, n plus 1, n1 for n equals 2. Also proven easily. Seems like a useful inequality step.
Right. And the third?
The third was n plus 1, n-1 for n-3. 3. Now, this one looks a lot like the original problem, and interestingly, the agent didn't manage to prove this lemma directly.
Huh. So it wasn't useful.
Well, even though the third one wasn't proven, the first 2 were crucial. The paper notes that the specific n3 base case from the first lemma showed up explicitly in the final successful proof's reasoning. And critically, the strategy of using mathematical induction was clearly identified this time around. Plus, the technique used to prove that second lemma, that inequality, it was explicitly applied within the final proof of the main theorem.
So even though one lemma wasn't proven, the other 2 unlocked the structure and the method needed.
Exactly. Comparing the successful run with lemmas to the failed direct attempt, the difference was stark, according to the paper. The direct attempt had no clear sign of using induction.
It really shows how that lemma generation can uncover the right path, especially when the strategy isn't obvious up front. It's like the agent figured out the key ingredients by proving simpler, related facts first.
Precisely. And this seems particularly effective for certain types of problems. The paper mentions Prover Agent performs really well on Olympiad-level problems.
Better than bigger models, even.
Actually, yes. In that specific category, Olympiad problems, it apparently surpassed the much, much larger 671 billion parameter DeepSeek Prover V2 model.
Wow. Even though that bigger model presumably used way more compute, more attempts.
Right. Which strongly suggests that this coordination, especially involving the natural language informal reasoning part, is really key for these kinds of highly mathematical, creative problems. It's not just about scale.
That's fascinating. And something else that seems really compelling, thinking longer term, is the design itself. You said it's modular.
Yes, very much so. This isn't one giant monolithic AI trained end-to-end. It's a framework. It combines existing separate LLMs and formal provers without needing complex joint training.
So you can swap components in and out.
Potentially, yes.
Bro.
Which means, as LLMs inevitably get better and better,
Prover agent could immediately benefit just by plugging in a newer, better LLM component.
that's the idea. It makes the whole system inherently scalable and adaptable to future advances. It's designed to stay at the cutting edge more easily.
That's really smart engineering.
It is. And the potential applications go beyond just math competitions, right? Nothing in this pipeline seems fundamentally limited only to math problems.
So you could apply this to other areas needing formal proof, like verifying software, or maybe even complex scientific theories.
Potentially, yes. Think software engineering, learning theory, maybe even parts of physics. Anywhere you need that rigorous, verifiable logic. Assuming the LLM component has the relevant domain knowledge, this approach could, in theory, help construct entirely new, verified theories without that risk of LLM hallucination or subtle logical flaws creeping in.
Building knowledge you can absolutely trust.
That's the promise.
Okay, so let's try and sum this up. We've been diving deep into Prover Agent. It's this AI framework that cleverly uses LLMs for the informal brainstorming and reasoning part.
Right, the intuitive part.
And then uses formal proof assistants like Lean for the absolutely rigorous verification part.
Leveraging the strengths of both.
It's achieving state-of-the-art results in automated theorem proving, doing particularly well on tricky problems, and importantly, doing it really efficiently compared to previous methods.
Especially impressive using smaller language models.
And that leads us maybe to a final provocative thought for you, the listener. This Prover agent. Its reasoning process seems strikingly similar to how human mathematicians actually work, doesn't it?
It really does. Exploring specific cases when stuck, hypothesizing intermediate steps, getting feedback, albeit from Lean, not a colleague, and refining the approach.
So, what could this really mean for the future? How might humans collaborate with AI like this in really complex, logic-heavy fields?
Could it fundamentally change the speed of scientific discovery? Or maybe change how we build truly verifiable knowledge? Not just in pure math, but maybe software, complex systems, maybe even foundational physics.
Lots to think about there. Keep diving deep with us to uncover more fascinating insights.